Research and learning is usually guided by theories. And theories are a way of organizing facts about stimuli and responses into statements about causes and effects. We won't be focusing on a lot of theories in this set of videos, but we'll cover a lot of facts. Those facts will often have come from experiments, because experiments are a way of identifying causes and effects. Let's say that a big bunch of facts you've already got is telling you that active learning, which involves using the material you want to learn, maybe by explaining it to someone else or using it to solve a problem, seems to help people understand and remember the material better than they would just by studying in whatever way they normally would. How might you set up an experiment to test the idea that something about active learning causes people to remember more of the material they need to remember? As we covered in the previous video, you'll have to show that there's a relationship between the independent and dependent variables. And you'll have to show that nothing but your independent variable could be responsible for that relationship. There are several types of experiments. Regardless of which kind you decide to run, you'll need to identify an independent variable. In our case, let's call it type of learning. And you'd probably say your experimental group would be asked to do some kind of active learning exercise, and your control group would be treated the same way, but they wouldn't be asked to do active learning. You want to find out whether the effect of behavior differs across those two groups, whether the dependent variable is related to the independent variable. So the dependent variable might be grades on a test over the material they were supposed to learn. In addition to looking for that relationship, you'll also have to show that nothing could be responsible for the difference in behavior but your manipulation. How you do that depends on whether you're running a between participants experiment or a within participants experiment. It might seem obvious that you'd just have the people in the control group be the same people that are in the experimental group. Then you'd know that without you manipulating their experiences, those two groups of people wouldn't differ at all. They're the same people. So any relationship between their behavior and the way they've been treated has to be due to something about the different treatments. If you get the general logic of that, you're on the right track. But there can be problems with those within participant experiments, and we'll talk about one of them later. So what about the alternative to within participant experiments? Between participant experiments. In between participants experiments, you have different groups of participants, and each participant has had a lifetime of different, unique experiences, not to mention different personal characteristics that could make him or her behave differently from other people. So how can you take a bunch of people who are all different from each other and split them into two groups in such a way that those two groups wouldn't differ appreciably from each other? Fortunately, there's a relatively simple way to create two different groups of participants that would be, without your manipulation, at least roughly equivalent, on average, in their scores on the dependent variable, and any characteristics that might influence those scores. And if you take advantage of it, then you can be pretty confident that a difference in how these two groups behave after you treat them differently is due to whatever you did to treat them differently. And what is this miracle of science that allows you to be so confident that you're starting your experiment with two groups who are roughly equivalent in any characteristic that might influence people's scores on your dependent variable? It's random assignment. Random assignment can be done in a lot of ways. For example, You could flip a coin each time someone shows up for your study, and if heads comes up, assign the person to your control group, but if tails comes up, assign the person to your experimental group. Or you could put a bunch of pieces of paper that say control or experimental in a hat. And when someone shows up to class or your lab or wherever they need to be, pull out a piece of paper and ask them to do whatever's involved in that treatment. In our case, any characteristic that might influence how well people do on tests should end up randomly distributed across the two groups. So differences between those two groups in those characteristics will be chance, random differences. Chance, random differences tend to be small. So you can be reasonably confident that the difference in test scores you'd find between your experimental and control groups without your manipulation would be relatively small. But the difference you'd get after your manipulation, if it actually affects people's behavior, should be big enough that you'll be able to say that it wouldn't have been likely to have happened by chance. In a between participants experiment, then, the participants in the control group may not be the same ones that are in the experimental group, but the only non-random, systematic, consistent, and substantial difference between them should be the difference in experiences that you created. For the study we've been talking about, you might randomly assign half the students in a class to watch videos like the ones you're watching and stop every time a heading changes to summarize what was covered in a couple of simple sentences. The other half of the students would just be asked to study the videos the way they normally would. If the difference in how much they know about the videos turns out to be a bigger one than you'd expect by chance, then you get to say that your manipulation had an effect. In within participants' experiments, the people in the control group are the same people that are in the experimental group. So whatever characteristics these people have that could affect their behavior would go with them from the control treatment to the experimental treatment. And so the only difference in what those two groups are like would have to be the independent variable you're manipulating. And any appreciable difference in how much they know about the material then has to be due to that difference in experience that you created. At least that's the logic behind running within participant experiments. Sometimes, though, especially if one treatment has to follow another one too closely in time, or if you're studying organisms that think too much, or all sorts of other reasons, the order in which your participants go through the baseline or control treatment and the experimental treatment could explain your findings just as well as the independent variable itself could. Let's say your participants studied the material for a week without doing any active learning, and then you gave them that test. The following week, they studied the same material using active learning, and you gave them the test again. What you would have inadvertently done is created more differences between the control and experimental treatments than you wanted to. After the control treatment, they'd studied the material once. But after the experimental treatment, they'd studied it again, so twice, as well as taking the test twice. So if they knew more after the experimental treatment, it might not be due simply to the act of learning, but to extra studying or having practice with the test. A common way to deal with what could turn out to be an order effect like this is to counterbalance. Counterbalancing involves making sure that any experience your participants will have that could affect their behavior gets deliberately manipulated so that its effect can be measured. For the study we're talking about, you'd have half your participants go through the conditions in one order and the other half in the other order. If they know more after active studying, regardless of the order in which they went through the treatments, then the order didn't have any effect. You can't get rid of an order effect by counterbalancing, but you can at least find out whether one is happening. So, in a within participants experiment, counterbalancing is used so that you can figure out whether any relationship you find between the independent and dependent variables can be explained by something besides your manipulation. And yes, it means that your experiment is at least partly between participants. Lots of the animal research on learning involves within participant experiments, assuming, not without reason, that the response being studied will come and go as treatment conditions change. And that allows meaningful work to be done with small numbers of participants, sometimes even just one, whose behavior is measured while they're not being treated in any special way. Then again, while they're exposed to whatever cause you think will change their behavior. And then again, at some point after the effect of whatever they were exposed to should have worn off. When changes in behavior go back and forth with changes in experiences, this kind of design can make for a compelling case that the effectiveness of the experimental treatment is what causes changes in behavior. So experiments are used to validate, or invalidate, explanations for why various learning phenomena happen, and find out what sorts of factors influence how or when they happen. From here on out, then, we're going to be looking at those phenomena. Let's say you've hypothesized that more appealing rewards cause faster learning than do less appealing rewards. So you set up a within participants experiment in which you time how long it takes rats to run through a maze to get food. What would that experiment look like? What would the independent and dependent variables be, and why? What would happen to rats in the control group? What would happen to rats in the experimental group? In psychology, theories organize facts about behavior into propositions about cause and effect relationships. But you can't find out whether those relationships are real just by seeing whether the behavior you're interested in shows up when the cause is around. Maybe the behavior would have shown up anyway. By starting out with groups of subjects that are equivalent in any characteristics that might affect your dependent variable, and then creating conditions that can tell you what behavior is like when the cause isn't around for one of the groups, and what it's like when everything's the same, but the cause is around for the other group. An experiment can show you whether there's a relationship between the independent and dependent variables and allow you to claim that it has to be a causal relationship. In a between subjects experiment, you create two equivalent groups by using participants who've been randomly assigned to one of your conditions. Random assignment should leave you with only small differences across those groups and whatever characteristics are relevant to your study. Then by creating one systematic, non-random difference in the experience those groups have during the experiment, you can show that that difference in experiences is probably the cause of any big, larger-than-chance difference in behavior that shows up later on. In a within-subjects experiment, you use the same people in both conditions. So nothing about the people themselves can be responsible for differences in the two groups' behavior. And you can find out whether there's an order effect by counterbalancing. Let's say you've hypothesized that more appealing rewards cause faster learning than do less appealing rewards. So you set up a within participants experiment in which you time how long it takes rats to run through a maze to get food. What would that experiment look like? What would the independent and dependent variables be, and why? What would happen to rats in the control group? What would happen to rats in the experimental group? In experiments, cause and effect relationships are represented by independent and dependent variables. The independent variable representing the cause and the dependent variable representing the effect. In this case, the independent variable would be how appealing a reward is. So, to do this experiment, you'd have to be able to manipulate whether these rats get a more appealing reward or a less appealing reward. Let's just say that we happen to know that rats like bacon, say, more than they like rat chow. The dependent variable might be something like the average length of time it takes each rat to run the maze 10 times. Being a within participants experiment, each rat is going to have to be exposed to the control condition and the experimental condition. So you might start by giving rats the opportunity to run a maze a few times, maybe 10 times, for a reward of rat chow. That's your control condition. While you keep track of the average length of time it takes each rat to run the maze. At some point down the road, the same rats have the opportunity to run a maze 10 times for a reward of bacon. That's your experimental condition. And you keep track of the average length of time it takes each rat to run the maze. If better rewards cause faster learning, then you should see lower average maze running times for the experimental group than for the control group. Couldn't hurt to counterbalance, though, running half the rats through the control condition first, then the experimental one, and the other half of the rats through the experimental condition, and then the control one. How could you sum up what this video says about experiments in just a couple of 3 sentences, like you would if you were talking to a 12-year-old? And of course, there's not a lot of detail in that condensed summary, but if you get the material, you should be able to see what sorts of questions would have to be answered in order to come up with a more thorough summary. Questions like, why do you want 2 equivalent groups of participants? What's random assignment?